And the last talk is by Matteo Lucchini, tracking the evolution of the compact jet across multiple microquasar outbursts with semi-analytical modeling. Go ahead, please.
Right, just waiting for the slides.
Assuming that the slide comes. Something is happening. No. We have no technical problems.
Okay.
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 Go on.
Thank you. And again, I want to thank the organizers again for finally managing to have a conference somewhat in person, but also for handling the hybrid aspect. So I'm Matteo Lucchini. I'm a postdoc working at MIT with Erin Kara, but today we'll be talking about a couple of projects that I did at the end of my PhD in Amsterdam with Sarah Markov. And I should say a lot of the credit for the work that I'm going to present also goes to Zheng Tao, who was a master's student who did his thesis with us and that me and Sarah co-supervised. And it will be about modeling compact jet in microquasars. Before I talk about the modeling, I just want to remind everybody that this jet coupling, or this relationship between the inflowing and the outflowing material, is something that you see in a multi-wavelength context. So the right-hand side plot is the radio X-ray correlation, which essentially shows some sort of tie between the outer jet and the innermost regions of the accretion flow, whatever may be happening close to the black hole. The right-hand side is the radio infrared correlation, which is interpreted as correlating something happening closer to the jet with what's near the black hole. And so to interpret this complex phenomenology, you really need the full power of multi-wavelength data. But also, of course, we know that it depends, this jet coupling depends on the state we're in. So the left-hand side shows a possible HID for a source, J1550. And we all know by now that the left-hand side states don't have jets and the right-hand side states do. Now, an independent way of categorizing these states that doesn't take into account spectral characteristics is in the right-hand side plot, which is called the color-color diagram. So what this does is it quantifies the shape of the power spectrum regardless of the normalization in the X-rays. And roughly speaking, states at the top left are states that have a flattish power spectrum, whereas states on the bottom right are more peaked. So what sources do is they go first count clockwise from the top left in the hard state down to the intermediate states at the bottom right, then they go to the soft state again, and then they kind of cycle back counterclockwise without showing any hysteresis. So this is an independent way of finding out where your source is, what state it's in without a hardness ratio, for example. So the model I'll be talking about is, of course, BHJET that Chiara just presented, but just to kind of remind everybody what's happening, this is, and the idea of this jet, of this model, is to really compare the innermost regions that are emitting in the X-rays with the infrared and radio emitting region further out. And to do that, we need to go beyond the Blandford and Konigal model, because the Blandford-Konigal model usually begins, let's say, emitting only from some specific acceleration region where you inject these particles. And so what we do is we inject thermal particles near the jet base, or what we call the jet base. In practice, it's more like, it's likely to be more or less what Matthew showed in his simulation, where it's some messy interaction between the jet edge and the inflowing material. But for the sake of simplicity, we're just considering the outflow here. And we include thermal emission from these thermal particles. They can scatter local synchrotron photons or disk photons. At some point, we accelerate this power law of particles, and that gives us the typical compact jet spectrum that we're used to. And so with this approach, we can really connect all these regions together. And of course, as Chiara mentioned, the code is now publicly available, and there is a very long and somewhat boring paper detailing all the assumptions we make in it. So the first source I'll be talking to is the one I personally worked on. It's called MAXI J1836. It's not a particularly famous source, but I think it's very interesting because it's the X-ray binary with the lowest viewing angle that we have found. So it's estimated to be between 4 and 15 degrees. So Dave Russell, somewhat optimistically for someone who used to work on blazars like me, called it a micro blazar. But if there is one source where you can really isolate the jet contribution, it has to be this one. And it also had excellent multi-wavelength data, for example, presented in Tom and Dave Russell's papers around 2014. And so what you see on the left-hand side is the HID of the source. So it was discovered in a somewhat bright hard state, and then moved to the intermediate state. And then this was a so-called failed outburst. So the source just went back down in quiescence rather than transition to the soft state. And you can see the evolution in the color diagram is kind of what I was saying earlier. So it started in the right-hand side, shifted down, and then went back counterclockwise to the top left. And then where Zhang's work comes in is he looked for a complementary sample of sources that had multiple epochs with good enough multi-wavelength data that we could actually apply the model to. And he did an amazing job just going through all these papers, all this literature, and all this data to find these appropriate sources. And the sample we kind of landed on are these three sources, XTE J1752, 1650, and Maxi J1659. And their progression in the HID and the color diagram is shown here. And in particular, what he did, what Zhang did, is he identified these three clusters of epochs in the color diagram that show very similar timing properties. And he jointly fitted these together to kind of constrain the parameter space of the model more and to have tighter constraints. So the kind of main result of all these multi-wavelength fits is shown here. So the left-hand side is one of the fit from Zhang's paper, which is submitted, should be published soon. The right-hand side is from my paper. And the first kind of big result is that there are two regimes to produce the X-ray emission. So in more fainter states, where the luminosity is in the ballpark of maybe 1% Eddington, we actually get this X-ray power law by scattering seed synchrotron photons, whereas the disk photons are a subdominant contribution. But the opposite is true for brighter intermediate states, where the luminosity is maybe more 10% Eddington or so. In this case, it's the disk photons that are dominating. And something else we found with these joint fits is that epochs with similar timing characteristics or similar hues can actually be fit with a similar jet-based geometry. And so what I mean by that is shown here. So the base of both, the x-axis of both these plots is the size of the jet base we infer from our fits. And the y-axis is this hue. So it's the location in the color diagram. So to just remind you, below 140 degrees is what we call the hard state. Some intermediate value, 140 to 200 or so is the hard intermediate states. And anything above that is the soft intermediate states where really the jet model stops being applicable. And you can kind of see that both for 1836, but also for all the three of Zhang sources, these two are correlated. And the somewhat straightforward way to interpret this is just by thinking about thermal comptonization. Epochs with higher U, so generally softer states, want a lower optical depth to produce these softer spectra. And so that can be achieved with a wider jet base. But in terms of fundamental physics, the mental picture we came up with together was thinking about Matthew Liszka's simulations from 2020, I want to say, when he first started showing these results on thin disks. And what he found in one of these papers was that as you increase the cooling in the disk and you reduce the aspect ratio to something like 0.1 or so, it is still possible to launch jets. But these jets are less collimated, they have a wider opening angle because the disk isn't exerting as much pressure on the side of the jet. So this is the kind of mental picture we came up with to interpret these results. And then a second result we found is that epochs that in the X-ray spectra require somewhat high reflection fractions are independent of U. But then a handful of these SCDs actually require very low reflection, and they're all close to the state transition. And of course, what it's reminiscent of is the behavior of Maxi J1820 that we've all been hearing about. And Sarah wouldn't forgive me if I didn't say this idea of the low reflection fraction, telling you something about the motion of your X-ray material is actually something that she mentioned in 2004. So the idea is if you're really seeing some sort of ejecta that's moving away from the black hole, the beaming is going to send all these photons away from the black hole, so you should get less reflection. So it's interesting to see that some similar behavior to these longer variabilization lags that our group at MIT found and that Barbara DeMarco found for 1820 in a somewhat different context. With the caveat that what we're doing currently with the reflection is not entirely self-consistent. We don't have these extended corona full GR reflection models yet. And then the last thing I want to say about this is, in principle, this could be testable with IXP if it's anything like, let's say, blazar flares that have these also bright X-ray flares that predate radio ejections. So my conclusions, I presented the first kind of application of the BHJET code, and we've shown we can reproduce the multi-wavelength SCD of both hard and hard intermediate states. And through these fits, the things we found is that first, depending on the states you're in, the brighter the source is, the more important this photons are for impulse Compton scattering. The fainter it is, the more important local cyclosynchrotron photons are. And additionally, we found that the the jet base seems to be correlated with the size of the jet base, seems to be correlated with the properties of the timing, with the shape of the power spectrum. And finally, in some of these state transition, it looks like some of this X-ray emitting material may not be very close to the black hole. It may be beaming away its photons away from the disk. So thank you very much.
Thank you. We have time for questions. Are there questions? Are people happy? You are happy? Last chance? No, I don't see anybody moving. So I think this means we have to move to the discussion section. Thank you very much again.